Okay, here's the good news today. I feel like George Bush. Whatever, there's no new taxes, right? There's no new calculus to this, right? This is sort of, what we're doing today is max min problems, optimization problems. So if we're taking what we've got, you remember like the problem, probably 4 on your exam, where I gave you those functions that said find the maximum and minimum on this interval. This is basic applications of all of this. So the calculus that we're going to be doing is actually pretty easy. There aren't any crazy derivatives where you have variable exponent, that stuff doesn't usually happen. The difficulty about this thing is actually stuff that ostensibly you've done before, and that is kind of setting up the work. So, without further ado, let's get some of this taken care of. So here's kind of a beginning. A farmer wants rectangular green. So let me kind of write a picture. So the farmer's got a certain amount of fence, and he wants to make a rectangular pen to put his, maybe pigs and cows and chickens or whatever he does in here. The farmer has feet of fence. How can this maximize area of 3 equal area? Right. So this farmer's only got so much fence, and he wants to make something like this. So he can put 3 kinds of different animals. And he wants to make the area as big as possible. Why do you suppose the farmer wants to make the area as big as possible? Right. He wants as many animals, and he wants his animals back. He wants them to eating off of as much ground as they can, right? So, how do we do this? This is an optimization problem. And like I said, in this, the calculus will actually be minimal. The trick is setting this up. So we'll see what we got. With these kind of problems, I'll always say that a picture is very important. Okay, there's my beautiful rendition of the 3 pins. What should I label? What can the farmer vary? That's right. I mean, he could stretch this out. He could make this mini contract blades, make it super long. Pins equal space like this, or he could make it super tall. By the way, notice that these 2 are kind of the same, right? So somewhere in the middle, you should be able to get this as big as possible. Well, let me call this distance. Let's call this X, and to make clear, let's call this Y. Right, that's basically the dimensions of one of the little 3 circles, right? There are many ways to do this. This is not going to be like this spot. Oh, sure, however you want to. You call variables. That's the great thing about math. As long as you don't break the rules, it's like art. It can be creative, right? Okay, so let's see. I think it's really important. This may sound childish, but write down your details. What are we trying to do? What do we want to maximize? We want to maximize the area of this whole thing. And what is the area of this entire enclosure? Right, and what is the width? X, right? What's the length of this entire enclosure? Everybody see where we got that? You got an X and then you got 3 lengths of Y, so this entire rectangle is. Okay, well, there's also another constraint here. Notice, in these problems, almost always what will happen is you've got too many variables. If you look at the title of your calculus book so far, it's called single variable calculus. You don't get into multiple variables until you get count 3. That's too many variables. We need to do that. There's almost always, you've got multiple variables you have over on the side. There'll be some way to get rid of them, and that is late one after the other. Huh. What other piece of information do we know about the farm? Got it. We've got his area. What else do we know? He's got feet of fence. And I did this P instead of a specific number, because this allows me to do interval in any property one. It can be 60, 100, 3 miles, whatever you like. Okay. Because the area is height times width and the total width is 3 wise. Okay. How many, what is P in terms of X and Y? And there's gonna be a foreshore for you now. Right, so his feet of fence, he's got 4 lengths of X this way, right? So we gotta use that up. And then how many lengths of Y does he have? He has 6. He's got 1, 2, 3 on the top one. Everybody up there? Now, what this allows me to do is this allows me to get Y in terms of X or X in terms of Y. Maybe because it's easier, I'll do this way. I want to write 4X is equal to P minus 6Y, or X is 1/4 P minus 3/2 Y. I solve for X and I'm going to put back in, you can solve for Y. This allows a new improved equation. Instead of X here, I'm going to have 1/4 P minus 3/2 Y. So I'll write it this way. I'll write it this way. Better 3/4 P Y minus 9/2 Y squared. Now, let me ask y'all a question. If I just walk up to you on the street, now remember, A is my dependent variable and Y is my independent variable. Here, Y can be anything. This function right here, you can plug anything you want into Y for, right? Here's an often overlooked part of these kind of problems. What is your playground? What are the values of Y that makes sense? What could the farmer do? How small could Y be? Six inches, half an inch. Actually, Y can be 0. The farmer would be awful stupid to do this, right? He's gonna have some awfully skinny cows trying to just run it like that, right? Because if Y equals 0, it's just basically a string, right? But he could do it. There's nothing that stops him from doing it, except maybe stupidity, but he could do it. here's the other extreme. How big can Y be? What's that? No, because remember, at the end of the day, you only got to be thick fence. It might help to look at this equation. How do you make Y as big as possible? By letting X be as small as possible. How small could X be? 0. So basically, the biggest Y can be is 1/6 B. And what happens in that case is a Y, a Y, a Y, and then a Y, Y, Y back, right? Everybody okay with it? So basically, the other extreme is when he stretches it all the way here, and he uses one length of Y, one length of Y, one length of Y, stretching it this way, and then he goes back. So you've got 6 lengths of Y, use up all his rope, and so, or his fence, and so each length of Y. Everybody okay with it? This is a continuous function on the closed interval. These are the easiest kind to maximize. What do? Take the derivative of this thing, round up your critical numbers, and just have the context. Now remember, P is just a number. The derivative of 3/4 Py, Y is the variable, P is the number, it's 3/4 P. The derivative of this, I guess, is minus 9 Y. And so, if I set this equal to 0, I get 9Y is 3/4 P, where I get Y is 1/12. Now, let's test this, and let's see what our answer looks like. You gotta have the content, because this is the only critical number. Now, let me ask you this. When you do these kind of problems, you have to test the critical numbers, and what else do you have to test? The endpoints. And you know what, the endpoints, think what are the endpoints? They're those two, right? I will tell you what you have to get. You're going to get 0. I promise you. Because when Y equals 0, it's tall and skinny, no width. When Y is 1/6 P, it's got no height. Right? But you can see this directly from the function, right? When you plug in Y equals 0 to here, you get 0 clearly, right? When you plug in 1/6 P, this term gives you 0 because 3/2 of 1/6 is 1/4, so this term is 0. This is also 0. So this makes sense geometrically, and it makes sense when I plug it in here. Because when I plug in 1/6 P here, 3/2 of that, I get 1/4 P minus 1. Everybody okay so far? So if I plug in this critical number and I get something that is bigger than 0, that's the maximum. This happens here. I get A is equal to 3 times 1/4 P minus 3/2 1/12 P times 1/12 P. That is going to be 1/4 of P minus an 1/8 of P. Is an 1/8 of P. Which is 12. So the area is equal to, 1/32 squared. And here's what it'll look like. For farm. And by the way, y is 1/12 feet. And so x is a 4th feet minus an 8th is an 8th feet. So this is 1/8 feet. 1/8 feet, 1/8 feet, 1/8 feet. And 1/12. So notice that he uses 1/2 of this entire fence going this way. And he uses basically in this direction, he uses 1/4. So actually it'll be thinner this way, right? Because this length is a 4th of what it's got. This length, oh, I'm sorry. This length is, like a 4th. So of course, it's longer this way. It's twice as long this way as it is this way. Right. Right. So, okay, any questions? Okay, I'm gonna do sort of the same problem from 2 different perspectives. It's similar to this one. Suppose I have a rectangle of this perimeter. Area of rectangle max. What does it show? So describe what this rectangle looks like. It's got maximal area. Now, if I have, say, a rectangle that's this perimeter here, notice I can make it, if I've got the same perimeter here as I've got here, I can make this a little taller or less wide. I can make it very, very short, very wide. I can push it up until it's a square, then I start making it very, very thin but tall, right? What do you suppose the rectangle maximum area is? No, there you go. Because actually, that's a good question, but I can run this out really far, but it's so tiny, the area is small. But notice for every rectangle like this, there's one like this. I would think that right in the middle where you can square the areas. But we'll figure that out. So let's set up the problem. What do we have? Problem says I've got a rectangle. And I don't know much, but I know that rectangles have a base and a height, and this is y, and this is also x as well. What is the perimeter of this rectangle? Good. And that's fixed. And what are we trying to maximize? And what is the area of this said rectangle? Yeah, it's just. How many variables do we have here from the thing that we're trying to maximize? Two. This is usually a hint that we've got to get rid of something. But this thing right here affords me the chance to say replace y with x. So if I solve this equation, y is 1/2 p times x. So my improved area is that. So now I am trying to maximize the function a is 1/2 px minus x squared, where p is a constant. Now, what should I be thinking about at this point? I've got my function that I'm trying to maximize. Right, we'll have to get to that, but don't forget this. Very easy to do this. What is your playground? What are the values of x which are relevant? How small can x be? Actually, it could be down to 0, right? I mean, it's the stupidest rectangle in the world, because it ain't gonna fit, right?
So. The way X, I guess that'd be with can be zero, but Y cannot.
No, why would we do that? Right, because it's the other extreme. I mean, we can get into semantics argument about whether that's a rectangle or not, which is kind of different, right? But you could get arbitrarily close to 0, right? Agree with that? And, but because this perimeter is fixed, your height's never going to exceed, y. Well, I'm sorry, your height is never going to exceed half the perimeter, right? So imagine being this thinner and thinner, stretching taller, it's got enough limit. There's no harm in putting x here because it doesn't make anything, you're not dividing by 0. How big can this be? So take the other end of this. You're close. Let x be 0. How about that? And the reason I like to take the extreme values of x equals 0 and x equals 1/2 p, where you've got degenerate rectangles that aren't really much rectangles, so line segments, is this allows me to do a continuous function called identical, and that's the best kind of max to do. So the derivative now is 1/2 p minus 2x. So set this equal to 0. I get x is 1/4 the perimeter. Now all you have to do is check again the endpoints, and then check this critical number that we found inside there. But if you plug in 0, you get 0. If you plug in 1/2 p, you get 0. And that makes sense because the two extreme versions were just line segments. They shouldn't have any area at all. And if you put in 1/4 p, you get 1/4 p, and you get 1/2 minus 1/4, which is another 1/4, and you get 1/16 feet squared, which is bigger than 0. So maximum area is 1/4 feet, 1/16 feet squared, and in this case, X equals 1/4 perimeter, which is Y. Because if you put in 1/4 perimeter here, you get Y is also in. So we get the square. So, this is a simpler version of the earlier pin problem, in the following sense. So if you have feet of fence and you're just making a single pin and you want it to be a rectangle, if you want to make the area as big as possible, well, make it a square. All right, I'm going to do another problem that is related to this, but it requires a slightly different technique. Suppose I have a rectangle of fixed area. A. What is the shape of such a rectangle with smallest perimeter? Okay, so let me contrast this example with the last. And the last one, what I had is I said, okay, I've got a fixed perimeter. I've only got this much fence, right? How do I make the area as big as possible? This is the flip side of the problem. Now I'm saying, you know what? I want to have this much area. This is how much land I've got. A. I want to mark this off as my rectangle length A. How can this be arranged so that the perimeter, the amount of fence I need, is smaller? Now, given this problem, I'm guessing the answer should probably be a square again, right? But let's see what happens. So now I've got fixed area A. Get some rectangle. And that's fixed, right? I won't keep the area the same. I can make it tall and thin. I can make it short and fat. I can make it in the middle somewhere, but my area is always the same. And I want to minimize what I want to minimize. So this is a little different. Okay, this is the thing that I want to minimize and this is a derivative of. So let me ask you this. What do I do now? Okay, good. I gotta get rid of one of these. Too many variables. And this time I'm going to use this equation here. Let's say that y is a over x. So now my p function is 2x plus 2a over x. Now, what should we be thinking about now? That's right. We need to think about our playground. what values of X are okay? Right, you can't be zero now, right, for the previous one, because there's clues for this. Your area is bigger than zero, right? It's got some positive area. What happens if you let X be zero? Yeah, then A is zero, that ain't gonna work. Here's another big fat hint. Look at this right there. You're gonna have a serious problem with X being zero. But there's no limit to how small you can make it, right? You can make a teeny tiny little X, well, X. And you can make this be 100 square meters or whatever, if you just make it quite tall. Agree? So there's no limit to X. And by the same token, there's no limit to how wide you can make X, right? You just have to make Y small enough to make the area small. Right? What's different about this problem? Right, you're looking for the smallest. There's also something else different. What was true about the last two examples was we had a continuous function on a closed interval. Here we have a continuous function on this interval, but it's not closed. In fact, it's an infinite interval. So you can't test the endpoint. This is another reason why it's important to figure out what your range of values is. You can't just do this thing where you test the endpoints and test the maximum and go, hooray, grab that each. At the end of the day, we need to be able to argue that this is in fact a minimum. And I'll take you through that. Okay, so here's the situation. This is our function. This is our interval. Since X is bigger than zero, this is continuous. Let's take the derivative of this and see what we can find in the way of derivative. Derivative of this is 2. And this is 2a x to the minus 1. So x. Now, I start to hunt for critical numbers of this thing. And of course, the first thing that leaps out at me is x is 0. That's certainly going to make the same time. But then I say, hey, x is positive. You don't have to worry about that. It's not an issue. So we're going to set this equal to 0. Figure out what's going on here. So I get 2 minus 2a over x squared is 0. So I get 2x squared is 2a. I take this over here and multiply by 2 squared. I take the square root, of course, I get 2 square roots of a. Sorry about that. That's better. But one of these I can toss, right? Because this one right here is not in our playground, right? Our playground is x is bigger than 2. So I only get one critical. The only relevant critical number is x is square root. Right. Now, here's the $64,000 question. Is this a max? Is it local? Is it absolute? Is it a min? Right? I mean, wouldn't it be embarrassing if this is max? How do we do this? Does radical A correspond? And if so, what kind? Well, let's go back. Let's go back to just like with curve sketching. What do we do with the derivative in curve sketching? We make a sign chart and try to figure out where it's going up, and going down. Here's my range. This is my playground. This is all I care about. Is X is zero, is beyond zero. So if this is zero, we don't need to count this. There's one critical number and it's somewhere here. All I care about is it's positive. Now, let's look at the derivative. This is kind of a good exercise in testing. Let me ask you this. What happens to P prime as X goes to infinity? As X gets bigger and bigger and bigger and bigger, what happens to this? If this piece gets closer to zero, so the whole thing gets closer to two. And I don't know much of two is positive. So toward infinity, this is positive. This is the only place it can change signs, so it's always positive. What happens is that it's very, very close to zero from the positive side. Very, very, very tiny number, 0.0001. What's true about this number? It's eventually negative because you get two minus, it's going to be a cube, that's a positive numerator, that's a tiny positive denominator, right? So this is a huge positive number, 2 minus huge positive, negative. So what happens here? This is a local min, right? Right. But it's also an absolute. Anybody tell me why? What's that? Well, basically, it's because it's the only one, right? So here's the deal. This is the only place where you care about the function. What is this telling? I'm not gonna be able to draw this perfectly, but it doesn't matter. It comes in and it hits this local minimum right here. And then it goes up forever. It goes down till it hits it, up forever. That you're not getting any lower. So this is an absolute. Because there's only one critical number on the relevant. Am I okay? So what was it? X equals square root of A gives absolute min. And I claim this is a square, because notice that y is A over X, which is A over square root of A, which is square root of A. So again, we get square. Okay, any questions? Here's one. Square. Perfect. And what you're going to do is construct box by cutting out four equal small squares. From the corners. Oh. So let me draw you in the next one. So you take a square piece of cardboard and you cut 40 squares on the corner. It's Well, these are supposed to be equal size. You cut these corners away. You get some of this. You get something like this. And then you fold it up. You see what we're doing? So it's like an art project, right? Maybe you work for Amazon, you get a square piece of cardboard. You cut these four corners out and you fold it up so it makes a box. What do you suppose I would like to maximize? I probably want to maximize what I can stuff in that box, right? So how about the volume, right? So that's the idea. How do I cut these corners away to maximize volume? So here's the big question. How? Make cuts out of corners. Maximize volume of resulting box. This is actually a really practical problem that you consider, right? You want to take this flat piece of cardboard, or fold it up, tape it up, attach it, however. How do you do this so that your box contains the maximum amount of stuff that you mail out, right? So this calls for a picture, right, beyond my diagram here. Okay. I didn't say anything about the side length, so I'm gonna call it something. Side length is A, that's gonna be fixed. This is a square, so this would be A. And I cut four corners out of this. So I'll label this. These are all supposed to be quite good next to each other. Do a good job. Equally, but nonetheless, they're good. And you guys can see that you cut these corners out. And fold. Okay. We want to maximize the volume in terms of how big of the X we cut out, right? See, when we fold this box up, by the way, if I have a box here, the volume of that box is just the area of the base times the height. And for this particular box, what's the area though? What's the shape of the base? It'll be a square, right? Okay, so what's the height of this box when I fold it up? The height is X. What's the area of the base? Let's see, this is going to be the base in here. Everybody agree that base is a square? So what's this length right here? Right. This length right here is A minus 2 lengths of X. Agree? Because you pull two of these off of it. And so, right, the base, the area of the base. And there's your ball. So I've got volume is X times A minus 2X on the square. What should I consider now? All right, but don't forget your playground. Once you have your function of one variable that here, it's very important, I think, to record what values of X are appropriate to this problem, right? I mean, if you just kind of plow ahead, maybe there's a negative critical number and you tell, oh, you just make a negative out of this. Or something like that. What's the smallest value of X? 0. What happens if X is 0? You haven't cut anything out of the box, you can't fold it up, and the volume becomes 0, because what you've got is a square cardboard sitting on the floor, right? It'll be volume 0, this is not gonna be the answer, but you could do it. How about the biggest? It's too much, remember, you gotta cut twice. I think you're on the right track. What's the biggest cut?
A minus X or something like that.
You're on the right track first. It's simple than where you're going now. So you make bigger and bigger cuts. You make a bigger cut, it'll look like this. Now you've got a bigger X. How far can that go before you're out of the box? There you go. Right, because if every X is 1/2 A, here's what you do. You come in and you cut your cardboard box and throw in 4 things, and you've got nothing left. And you feel like a total tool because now you've ruined the box. But you could do it. You've got nothing left, so the volume should be 0, but it can be done. And I'm digging on this because I've got a continuous function on closed interval. So all I have to do is take a derivative and test any critical numbers versus the inputs. Everybody okay with this? So B prime, taking the derivative of the sucker, what rule do we got to do for this? We got to do the product rule. So we got 2 pieces. We got this times this. Derivative of X is 1 times A minus 2X squared. Plus X comes a derivative of this piece, which is 2 A minus 2X times -2. Now, one of the biggest struggles that most folks have in this class, not just this class, but on 2 calculus classes with the algebra, right? Because what are we going to do now? We're on a quest for the critical number. We got to know whether the derivative is 0 or does not exist. This one will never be it does not exist. Goodness, what is this? Does anybody see something to do with my? There you go. That's a great idea. So let's do that. Notice that both of these pieces have a factor of 8 minus 2x. So let's jerk that out. A minus two X. Or you can pull it out here, and what's left over here is just, what is that, negative four X? So this is going to be A minus two X. And it's going to be A minus six X. I'm digging on this, man, that's too easy piece. A lot easier. All right, it's easy to figure the critical numbers out, if I set this equal to zero, I get A equals one half. X equals one half A, and X equals one sixth. Everybody with me on that? So I get two critical, I guess I should probably check, are these both in our playground? Sure, this is the big, right, because this one's a third the size of this one. This one, one half A, in fact, doubles up as an endpoint, so that's one less thing to check, right? And this one is certainly smaller than this and bigger than zero, so both of these critical numbers are germane. Let's see what happens. Let's one half A, volume one sixth A, volume. When I put in zero, I get zero. When I put in this, I get zero. Because when I plug in zero to volume, I get zero because of this. And if I plug in X equal one half A, I get A minus A, zero. And of course, again, this makes sense because if you think about this geometrically, physically, however you want, think of it, cutting nothing out meant that I just let the particle square and it's flat. It's got area, but it holds nothing. And this one meant I cut the entire box away, threw it in garbage, so it holds nothing. So that makes sense. What happens here? This is one sixth A, and A minus, let's see, twice of this is one third A on the square. So that's going to be two thirds A squared. So that's going to be 4 9s 6, 2/27. Yeah, I get 2/27 A cubed, bigger than zero. So that's kind of nice. Got a formula in terms of how big my, whatever the length of that particle inside is, just cube it, multiply that by 2/27, and that should give me my maximum volume. Right. And your X should be 1/6 of A. So in other words, you go a sixth here and a sixth here, and that'll be where you maximize your profit. Okay, any questions? Okay, here's another one. How many of you have ever gone to the grocery store? Grocery store. So if I took the label off like a can of green beans or a can of corn or a can of soup, you might have a hard time telling the difference, right? Have you noticed the shapes of the cans are all the same? I mean, forget the fact it's a cylinder, but how many of you have ever seen a soup can that's that thick, 10 feet tall? Or one that's as wide as a manhole cover, but on that novel. Now, of course, there are practical reasons, most can openers are designed to deal with that, and of course, that would be a problem on store shelves. But have you noticed that even among the varied size, sometimes you see an outlier, but there are a lot of ends, they're the same shape. Ratio of, say, radius to height. Why is that? So here's the problem. I am making can. And I want my can to hold something. Green beans, motor oil, whatever. The cost, specific. Circular cylinders. So it's kind of candy expect from soup. for example. The cost of making the top and bottom is twice the cost of making circular siding. And this cost is per unit. The cost of making the top and bottom is twice per unit area as making the can. So the side is sort of cut out of something. It's harder to cut the circles, and they always see that with the ripples and so forth. What is the ratio of radius to height of the cheapest can I can make? One can imagine this is a kind of a practical real world problem. You know, you're somebody that does operations research or something like that. Your boss comes to you and says, "Oh gosh, we've got all this great green bean and motor oil leaks that we've got to get out on the market. I need a can, right? And I want this can to hold a specific volume, right? So can holds some fixed volume. Because maybe you want a 16-ounce can of soup or a 2-quart container of motor oil. You give out whatever your product is in this specific volume. You don't want to change that. So you need to make a 2-quart can of motor oil, or you need to make a 16-ounce can of soup or an 8-ounce can of green beans. It's going to cost me, I know that my production cost for making the top and bottom of that can are going to be twice per unit area. What makes the side? I give to you the problem of tell me how to make that can. So that can holds the volume I want and as cheap as possible, right? We all understand the motivations from profit, right? Make that can as cheap as possible. I'm gonna make as much money off my green beans and motor oil, right? So it is time for us to be calculus heroes and figure out how to make a lot of money. So start with a picture. We'll make some can. It's going to be a circular cylinder. I can vary the radius. And I can vary the height. But what I'm stuck with is my volume is constant. So in other words, if I make that radius thinner, or if I make that radius smaller, I gotta make it taller. If I want to make the can shorter, I've got to make the radius bigger. And by the way, what is the volume of this can? That's right. Any cylinder like that, its area of the base times how tall it is. The area of the base is pi r squared, agreed? And the height is h. . Well, now, here's what I wanna do. I wanna maximize cost. Now, what's one thing that I didn't say in the problem? Now, I didn't tell you what the cost was. The only thing that I told you was making the top and the bottom was twice as much as the pot. But I didn't tell you how much it costs, right? Should it matter? It should not matter. And actually, we will see in the problem and it does, it should not matter. Let me be super careful and we'll say, suppose it costs. So it wasn't told to me. Again, this is math. Use your brain. Suppose it costs a cents per unit area. Well, suppose the cost is a per unit. Side. Right? And so it is going to be two A per unit area. Because top and bottom are a little bit more expensive to make. Let's see the cost might be. Let me do this. What is the cost of making that top? That's per unit area, right? So it's 2 A per unit area. What's the area of the top? Right. Right, Rick? Just to make the top, so area of the top comes 2A, right? Cost of side. Same principle, it's going to be A. What's the area of the side? This is really not so bad to figure out. Imagine that I take a pair of metal shears. I cut this soup shell. And then, now that it's cut, I can roll it out, pound it flat on the paper, right? And it will look something like this, won't it? Everybody agree if I unroll that thing, right? It's like unrolling like one ravel of toilet paper. It's gonna look like a rectangle, agree? And it's gonna have height H. And how wide? Close. It should be the circumference, so. Right, agree with that? So the area of the side should be 2 pi. Let's see the total cost of 10. It should be the cost of the side, which is 2 pi A or H, plus the cost of the top and the bottom. So I get 4 pi A. But here, there's two of these, we've got top and bottom, for the 4 comes. And the cost of the side. Right, picture. Now, what problem do I have with this juncture? got too many variables on it. I've got variable R and A. Remember, A is just a constant. It shouldn't matter. But R and H vary. How can I get rid of one of them? No, because that'll just give me the cost to zero. I've got another equation. There's something that I haven't, I've got the cost here, but there's something else that's remains a problem. Can I make this can of any volume? This can has to be its constant volume. So I can solve for H, or I can solve for R, and substitute back in this equation. Now, which would you rather do here? Would you rather solve for H and plug in for H, or solve for R and plug in for R? I agree with that. What do you see that makes this better? If you solve for R, first of all, you won't have to take square root, right? Because there's a single R right here, which is obnoxious. But see, solving for H is easy. There's only one H there, right? So let's use this equation here. And remember, this capital V is a constant. H is equal to V over R squared. So I get a new improved cost function. So let me clean this up just a smidge. This is going to be power. So 2AD over R. R's length up there. And okay, folks, what do you suppose we should do now? Very good. What are the acceptable values for R? I cancels this one out. And this R cancels one back. Okay, R has to be bigger than zero, right? Again, there's a couple of clues on this. Number one, look at this. R equals zero is a problem. And also, if you think about it, your volume here is constant, which I'm assuming is bigger than zero, because otherwise, why are you doing the problem? You can't hold anything. So it is impossible, if R is zero, for this to be anything other than zero, so let's call it C. How big can R be? Well, I don't think there's any limit to that either. If what you're doing is just trying to keep H constant, because you could make a soup can with R 7 miles long if you make H appropriately small, right? Nobody wants to take a 7-mile soup can and put it in their car, or a soup can that's 100 feet tall, but these things theoretically be made. This is one of the hard ones because this is continuous function on this interval. But there's no endpoints, right? So again, we're going to have to make sure we check to see what this is maximum. First thing to do, let's try to find the critical. Okay, remember R is my variable. This is two AV times R to the minus one, so it's derivative minus two AV over R squared. The derivative here is eight A. Now, again, an immediate looks like it could be a critical number that jumps out to me as R equals zero, because it makes that undefined, but again, it's not in our platelets. We don't have to worry about that. So all we gotta do, set this sucker equal to zero. See what it shapes out. I get. Set this equal to zero. Gosh, what a mess. Let's bring this over here. A R Q to A B. And notice there's an A on both sides that cancel out. I'm gonna take that as a separate step, because I think it's important. And this means that it doesn't matter what the cost is, your answer should be the same. This makes sense. It doesn't matter if my cost per unit area is $1, $2, a cent, whatever it is. To minimize cost, you should get that same ratio of radius of the height. Let me completely solve this. This is RQ is equal to B over 4 pi. Or what is this number? I don't know exactly, because after all, I don't know exactly what V is. But here's what I do know, it's positive, right? Because V is positive and 4 pi is positive, and Q root is all positive. How many critical numbers did I get in my range? Just one, right? So we need to test. Test it, right? Because what did your boss tell you to do? Your boss said, we're selling our goop in this can, and I want you to make the cheapest can. I want you to minimize the cost. What if that gives you a maximum? And you tell your boss, make the can this way, and he is spending as much money as possible. You are so fired, right? We better make sure that this is actually giving us a minimum, right? So. How much, I know it's positive. Now let's look at C prime again. This was two AD over R squared minus plus 8 AR. Now, again, with the derivative, I've got my A back in there, but I do know that A is positive, right? It's not going to be a negative cost per unit area. Otherwise, I just make hands and make a living off of that if somebody's paying me to do it, right? So, what happens to this animal when R gets very, very, very large? For very, very large value of R, this is a huge positive, and this is almost zero. So on this side of the critical number, it'd be positive. What happens when R is very close to zero? This is a huge negative number, and this is almost zero. So this gives a local and absolute. down, and then it goes. So minimum occurs when R equal to Hebrew, B over 4 pi. Now, I did ask what the ratio of the height was, so I found the existing code. Remember this one? All right. And let me remind you what B was. This is B times R squared. This was right. I put the 4 on the top instead of bottom, for some crazy reason. So I have R cubed is equal to B over 4 pi, which is pi R squared H over 4 pi. So cancel the pi, cancel 2 R's, we get R is H over 4, or R over H is 1/4. So if it costs twice as much to make the top and bottom as it costs to make the side, you should make it so that the can looks like the height, the radius of the height, should be 1/4. So the height should be 4 times whatever the radius is, or twice the diameter. So it should be like this, like. So in other words, the can should be about twice as tall as it is wide. And that's probably pretty close to what we used to see in grocery stores, right? Any questions? Okay, any questions? If they perfectly circular. Obviously artificial one. And a radius 2 miles. One, yeah, from where you are on the shore to the exact opposite side. And row at 2 miles per hour. And walk at 4 miles. What have, what course should you take? Minimize your time. Okay, so here's the situation. There's this perfectly circular way you want to get around, it's the opposite shore. It's like this. Now you're here. You want to get right here. Radius of this way is 2 miles. And you have a rowing / walking option. Right? So one thing you can do is you can walk around the lake. Another thing you can do, and it's obviously a shorter path, is you can row straight across it, right? What other options do you have? I didn't make that clear in the problem. I wanted to see what you all. What else can you do? I think we're also going to do that. Yeah, you certainly can swim. But I mean, so you've got a boat right here. You can boat straight across. You can walk across. What other options would the boat have? Well, you could certainly do that, but that's going to take longer, right? Because you clearly, one thing that you could do, you could do this. Instead of going straight across, you might go there and then get out and walk, right? So you could both here and walk, both here and walk, go all the way across. You could just walk. How do you do this to minimize time, right? Because you want to get over there to the full cookout as soon as possible. So, how do we do this? What are we trying to do? We're trying to minimize. So I want to mark our path in black and blue. We're going to do this. Is there something else that I might label on here that might help me with it? Great idea. Let's do that. Now, let's call this distance B for boat, and this distance W for walk. I like to do things I remember here. So, when my time taken, okay, on this black path, how long does it take me to boat this distance here? So I'm going at 2 miles an hour and I'm going B miles. So time taken on this is B over 2 hours. Everybody agree? How about W? Okay, so total time taken is B over two plus W. Do I agree with that? Okay, this is a baby step, right? It's a, and I encourage you to do this, when you work, break this into the digestible pieces. So what I've got here is, right, it's just not super helpful yet. Because I don't really have a good feeling what B is, what W is. Maybe something. Maybe it's- By the way, this is also material. Like this radius and stuff. So. Can you mention what that is? Uh. Well, yeah, but, what's that? Well, it depends on what theta is. I mean, if I collapse theta into small, can you find this in terms of theta? Let me ask you this. What's that? Notice, this triangle is isosceles, isn't it? Right? And so shouldn't that mean these two angles are the same? Can you tell me what the same is? There you go. How'd you know that? Well, so let me put it this way. This angle plus this angle plus this angle should be 180. And this angle plus this angle should be 180. So this should be whatever these two add up to. Okay, where do we go from here? Um, so run that by me again.
Got two sides.
Okay, hang with my definition. So you're on the right track here. So let's look at what that is. We'll do that first. You better remember what this length here. You have a circle of radius r. You have this little wedge in the 5 theta here. You know what this length is? The way I always remember this is if theta is 2 pi, you should get the entire circumference of the circle. Shouldn't you? And if you put in theta equals 2 pi, you get 2 pi r. If theta is pi, you should get half the circumference. So very good. So W should be what? two theta. What about this? Someone said it earlier, that's one way to do it. Somebody suggested like a lot of persons. Yeah, I think you did this for a lot of persons. Because we know that this angle is what, pi minus two theta? Everybody agree with this? So law of cosines. So if it's two, b, and this is pi minus two theta. That's enough information in the answer. So let's see what we got here. B squared, doing the law of cosines. Two squared plus two squared. This squared plus this squared minus two times cosine of pi minus theta. So it's rather intimidating, but I think this is going to be 4 and 4 is 8. It's going to be minus 8. And cosine, let's see, cosine, sine. So the signs are gone. So it's going to be minus. So this is going to be cosine. Oh, yeah. This is going to be, 2, 4, equal to 2. Okay, and I'm gonna work this out a little bit more. B squared is 8 plus 8. Cosine 2 theta, one of the identities that I gave you was, 2 sine squared theta minus 1. Actually, yeah, there's an easier way to do this too. So this is going to be 8 plus 16 sine squared 2 theta minus 8. Then, so I get b squared 16 sine squared 2 theta. So I get b is 4 sine theta. Yeah, and there's definitely an easier way to do. See if you can get this. That'll be a good exercise for you. So what I get is a b is 4 sine theta. This allows me to improve b over 2 is 2 sine 2 theta. And w over 4, what was w? 4 theta. Right, okay, so- Okay, so what are my relevant values? What's my flavor? How's my? Agreed. Can you interpret for me what that means when theta is zero? What are you doing? You're just voting straight across. How big can it be? Yeah, well, so think about theta. Right. Can you interpret what happens to theta's power two? What does that mean? You just walk, you ditch the vote and just walk. All right. This is all vote. This is all. Okay. So. The derivative of this is, oh. The derivative of this is, 4 cosine 2 theta. Let's set this equal to 0. The derivative of sine 2 theta is cosine 2 theta times 2. So 0 is 4 cosine 2 theta plus 1. And so 4 cosine 2 theta is equal to -1 or cosine 4. I'm gonna continue with this. So we got 8 plus 8 cosine 2 theta. Is that what I had earlier? This was 8. Is this what I had earlier? 8 plus 8 cosine 2 theta. Yeah, I think. So let me check this again. This is 8 plus 8. 2 cosine squared theta times 1. This is 6. This should actually what this should be is B should be 4 cosine theta. Yeah. And for some reason, I've got a 2 theta here. I messed that up twice. Let me ask you a question here. This should be 4 divided by 2, so it should be 2 cosine theta plus theta. Let me ask you a question. This is kind of what's tipped me off. What tipped me off about this that I had made a mistake earlier? If the cosine of 2 theta is -1/4, where is theta? It has to be out of range, right? This means that theta, well, two theta has to be over here, so I'll bring theta back, so this made me suspicious here. The actual, I messed up a lot, it should be, two cosine theta. Sorry about that flood there. It's two cosine theta. Plus theta. This would be easy. Cosine and double. I did it. There we go. If you set this equal to 0, I get 2 sine theta is equal to 1. Sine theta is 1/2. Anybody tell me where does sine theta 1/2 in our relevant range? Sine theta is 1/2, I guess it's power 6, isn't it? So let's test this. Only one critical number. Let's look at t of 0, t I over 2, t I over 6. And this illustrates the importance of the some stuff that I was talking about testing things. When I plug in t equals 0, or I'm not t, when I plug in theta equals 0, my equation, which actually turned out to be 2 cosine theta plus theta. What do I get? I get 2 plus 0 is 2. By the way, there's a good gut check. Theta equals 0 means that it's all both. I went 4 miles at 2 miles an hour. I got a 2. That makes sense. At pi over 2, what do I get? When I plug in pi over 2 for theta, I get 2 cosine pi over 2, which is 0 plus pi over 2. This makes sense as well, because how far do I go? I go halfway around a circle of radius 2, that's 2 pi, divided by 4 miles per hour, pi over 2. So far, which is better? Pi over 2 is better. It's a little bit faster than walking, straight. So, I'm enough faster at walking, right? What happens? Get 2 cosine pi over 6, which is radical 3 over 2, plus pi over 6, which is radical 3 plus pi over 6. Interpretation. What happens here? All right, you may not know this, you don't have a calculator or whatever. Everybody agree this is more than 0.5. And this is more than 1.7. 1.7, 1.5 is 2.2. What actually happened here? That's right, this is the maximum timetable. So if you want to get in your boat and go at pi over 6 and then get out and walk, that actually takes the most time, right? And what we're looking for is the least. What should you do? You should walk. Okay, any questions? I can't emphasize this enough. I'm gonna give you a quiz. I think the problems on this quiz, I've got 3 of these. They're in increasing order of difficulty. Go home and practice a lot of these.